Hello everyone, my name is Ben. What you are watching now is a course on calculus. In this course, I will try my best to make calculus more understandable. And today this is our second video. In this video, we continue with the area problem and try to figure out the exact value. We know for this purple area A, we introduced a method of building rectangles and worked out a general formula for the total area of these rectangles. We see SL is a numerical solution. We also made a guess in our first video. The exact value of A might be this fraction, might be 1/3, but we need a mathematical proof for such a claim. This video is about the proof. And before we organize the proof, let's just summarize a little bit for our reasoning. Here are some examples of our rectangles. Based on the construction, my first observation is this. All our rectangles just fall under this curve, right? So the total area of them, the left-hand sum, will be less than A, will be less than the purple area. This is a fact. No matter how many rectangles we have, there will always be a difference between SL and the number A. Second, we also notice that although SL is less than A, it is getting closer and closer. If we build more rectangles, and we can always build more. Just because we can build any number of rectangles, I would see here the total area, the left-hand sum, SL, can get infinitely close or arbitrarily close to the purple area A. Well, we have two simple facts about SL, very straightforward. And at the same time, we have this general formula. In this formula, we have two fractions, 1 over 2 times n and 1 over 6 times n squared. We know this fraction is always greater than this one, so SL will be less than 1/3. Second, when n grows, when n gets bigger and bigger, these two fractions will get smaller and smaller. And when n is very large, they will get very close to 0. As a whole, SL will be closer and closer to 1/3, right? And because n can be any natural number, I would also see here SL can get infinitely close or arbitrarily close to this fraction. Well, we get another two facts about SL. And remember, we can tell this from this sequence of values, right? But anyway, in total, we have 4 of them. Fact number 1, fact number 2, fact number 3, and fact number 4. And we have infinitely close here, we have infinitely close here. This is a new relationship, a very interesting relationship. Now our job is to prove this, the exact value of A equals this fraction using all these facts. The technique here, or the trick here, is proof by contradiction or proof by assuming the opposite. Here is the opposite. If we don't agree A is 1/3, if we think they are different numbers, there will be two cases. A is a number less than this fraction. A is a number greater than this fraction. And let's look at the left first. In this case, we assume A is a smaller number. I put both on the number line. A will be this point on the left. And we know SL can be arbitrarily close, can be infinitely close to this fraction. So if I put all the SL values on the number line, they will go like this. It means from somewhere, all the subsequent SL values will be closer to this fraction than number A. All the subsequent SL values will fall in between. As a result, SL will be greater than number A when we have enough rectangles. But we know this is impossible. All SL values are supposed to be less than number A, no matter how many rectangles we have. So we find a contradiction, we are contradicting a fact. This means the assumption must be wrong. We have to give up this assumption. This is the left part. Now let's turn to the right. In this case, we assume a is a larger number, so a will be this point this time on the right. Similarly, we know SL can be arbitrarily close to a, can be infinitely close to a. This means when we have enough rectangles, SL will get closer to a than this fraction, right? So we will have SL values greater than this fraction, and this is impossible. All the SL values must be less than this fraction. Again, a contradiction is identified. This assumption must be wrong. We have to give it up. Both assumptions are wrong. It seems we have no choice. A must equal 1/3. If we don't accept this, we will get contradictions. Okay, this is the whole proof. If you have any questions, just let me know in the comments. I will try my best to explain with more details. Now let's take a further look. In the left part of our proof, we used this fact, SL arbitrarily close to 1/3. This is our fact number 4, right? And we used this fact, SL less than A. This is fact number 1. And in the right part, we can also find fact number 2 and fact number 3. So our proof actually shows this. This assumption is not compatible with these two facts, fact 1 and fact 4. This assumption is not compatible with these two facts, fact 2 and fact 3. Now let's do more research. We still look at the left first. With this assumption, if we guarantee fact 4, if we allow SL to go arbitrarily close to this fraction, we will have this, right? As shown in the proof, we will have SL values greater than A. We have to give up fact 1. And now suppose if we go the other way, if we guarantee fact 1, what will happen? Well, it will look like this, right? All the SL values will be blocked, or bounded by number A. There will be a gap between SL values and this fraction. They cannot get arbitrarily close to this fraction anymore. We have to give up fact 4. Basically, with this assumption, we cannot avoid contradictions or conflicts. We cannot keep both facts. If we want to keep both facts, we have to give up this assumption. So with fact 1 and fact 4, A cannot be a number smaller. A must be a number larger or equal. This is the left part. Now let's look at the right part. It is very similar. With this assumption, we cannot guarantee both facts. I will leave the contradictions or the conflicts to you. Basically, fact 2 and fact 3 don't allow this to happen. They only allow A to be a number less than or equal 1/3. Put them together, we know that only the equal relationship can hold up. Well, I hope after this slide we can understand the facts better and we can be more confident to organize a proof by contradictions if required. Okay, now we can see this is not a guess anymore. It has been proved. In our proof, SL, the total area of the rectangle, the left-hand sum plays a very important role. We know the total area, SL, can never reach A or 1/3. SL is always less than them, but it doesn't matter. The special thing about SL is this new relationship being infinitely close or being arbitrarily close. From now on, if I have a sequence like SL that shows such a relationship, I will know being infinitely close or being arbitrarily close is a bit special. Such a sequence cannot get arbitrarily close to two different numbers, because otherwise we would always be able to find contradictions or conflicts, right? In other words, if a sequence is arbitrarily close to a number, this number must be unique. This is a big finding. In the future videos, we will try to formalize this as a theorem. I feel very proud we can come up with this. But now I think I can stop here for video 2 with this finding. If you have any questions, just let me know in the comments. I will try my best to answer it. Our goal is to learn calculus without any confusion. If you think today's video is a bit helpful, just give me a thumbs up. Okay guys, thank you for watching. See you next time.